Alrighty, well, we are almost down to the wire. So, I looked over and graded people's final SLP uploads, and those all look really good. Some nice work with those, some very cool projects. I will find time to start watching YouTube videos of people's uploads, and then I'll post grades for those, and that'll probably happen over the weekend, but I don't anticipate any issues with that. If you indicated that you're okay with having your video shared publicly, I believe we're going to put those together somewhere on engrcs.com, so you'll be able to look at your video and other people's videos, and I'll post information when I figure out the details of that. And that sort of is the stand-in for having the whole formal presentation in the digital lounge, which we couldn't do this year. But nice work on the SLPs. I think there was some good stuff that was done in there, and hopefully in the end people feel like it was worthwhile use of their time and energy. So any questions on anything? The final will be on Canvas, and I think it's going to be similar in structure to last time, with the midterm, where I'm going to have you basically type in code or type in answers in Canvas, and all the same stuff I said before still applies, right? Figure out a system that works for you so that you're not typing your only answer in Canvas, right? Type your answers up somewhere and then copy and paste. And if you can figure out how to make your code indent and stuff like that, stick with that. But you can expect requests to write some code, possibly entire program, or possibly just a method or two. You may see code and be asked questions about it. You may see code and be asked to modify it. There could be short answer, conceptual type questions. I haven't written it yet, so I'm going to write it over the weekend. But yeah, it'll be a Canvas quiz, and it will be Monday at 2 o'clock. And I'm only allowed to schedule an hour for the final exam, so it'll be Monday 2 o'clock till 3 o'clock. All right, well, so we didn't get through a lot of stuff I wanted to get through with Android yesterday, and I don't want to spend more time on that. I really just wanted to show you some basics of that framework. There's a whole lot more, but if you know enough to make a basic app and have it interact with a button or with touching the screen and so on, and that gets you pretty far as far as being able to read the documentation or look at examples of code, and get yourself into trial and error framework. I think the key to learning a new language or a new system or anything like that is getting yourself a sandbox, right? Getting yourself somewhere where you can comfortably start experimenting, right? Make some changes and try some stuff and see what happens, and answer your questions like that, and then maybe do some online looking for higher level information, like what's the whole idea here and so on. But if you can get yourself a framework where you can start doing experimentation, try things, see what happens, right? I think that's the best way to learn this stuff, because you read a book, you're taking in information in whatever order and format the writer of that book decided was most appropriate. if you're doing your own experiments, it's like, well, how does this thing work, you know? So you write some code and you start digging into it, and it's going to let you follow the path that your brain is naturally following on its quest for understanding, right? So so that was the main goal of talking about Android yesterday, was try to help you be at a point where you can start experimenting with things. And I think that works, you know, like I say, whether you're trying to learn a new language, you want to learn Python, get the basics, get yourself a Python interpreter, right? Get to the point where you can write, you know, a program, and you can write a few functions and then start experimenting with it. Play around with the language constructs and so on. And a lot of stuff that you'll encounter and want to learn about are going to be very similar to things you've already done, right? The leap from Java to Python is not that severe, right? The leap from C to C++, if you know Java, is not that severe. All right, so I'd like to take a look at, not Verilog, at some source code. So you can Google for the source code for Java, right? So so there's a version of Java called the OpenJDK. So I don't know if we've talked about this actually. There's sort of two branches of Java. When you're downloading and stuff, you'll sometimes see JRE and you'll sometimes see JDK. This is the runtime environment. This is if you're not writing or developing Java, you just want to execute it. Okay, that gets you the Java virtual machine and a few other tools. If you want to write code in Java and compile it and debug it and build archives and so on and so forth, you need the Java Development Kit, the JDK. That's what we've been working with throughout all of the stuff we've done this quarter. And there's a JDK from Oracle, but there's also an open JDK that's not proprietary, right? And since it's open, you can download the source code. And source code is fun, okay? If you want to really understand something, looking at source code is a really good way to sort of cut through all of the details. And it's nice because so much stuff is open source now, right? So for a long time, all of the internals of how an operating system was put together, how a compiler worked, and so on, those internals were proprietary. And the best you could hope for was to look at the binary code that was executing when, say, your operating system was doing something and reverse engineer it, right? Disassemble it, decompile it, and try to figure it out from there. Well, so much stuff is open source, including Linux, including Java, and so on, that we can learn a lot about these systems by exploring the source code. And again, if you have access to the source code, you can make changes to it. So if you have, you know, your own Linux machine, maybe running in a virtual box, and you want to tinker around with operating system concepts, you can take the source code for Linux and you can modify it. You can take the code for the kernel and you can make changes to it and you can see what happens. Or you can put things into the middle of it to monitor and give you information about stuff that's going on. And this is a fun way to do computer science, in my opinion, right? It makes computer science more of a lab activity than a sit down and read a book activity. Computer science should rarely be a sit down and read the book kind of thing, right? You should be typing away and you know, the screen flashing on your face and reflecting, and smoke coming out of the keyboard. You know, that's an ideal environment. So let's look at the source code for Java a little bit, and let's see what's in here. So I've already downloaded this, and it comes down as a big zip file, right? I did not mean to do that. Oh well. Meant to do an unzip-L and just do a listing of this. So it's 17,000 files. And everything that we can pull up documentation on, everything that we've dealt with in Java and a whole lot more is sitting inside here. So let's take a look in here. So under this Java directory, I have applet.io, language, math, RMI, util, right? When we say something like import java.util.linked list, right, it means that there is a directory Java, and inside there is a directory named utility, and inside there is something called linked list, right? And we can look at this code, and it's just Java code, you know. Yeah, guess what? Java's written in Java, right? What could be more natural? So let's take a moment and look at the commenting in here, right? So there's a big block in the beginning. This is what I would call a header block that basically says, you know, there's a copyright, who made this, right? But then says this is free software, you can redistribute it, it's under GPL2, and so on. And it points out that when you download this, you should also get a copy of that license, right? And there's contact information, and so on. So that's like a boilerplate header block that you'll see in the top of all these files. All right, package is saying that this should go under directory Java, subdirectory utility. Okay, and it's importing some other stuff. And here's a comment block that describes the class, right? So I've said when you write the code for a class, you should put a comment block in the beginning describing the class. Where here's the block that describes a linked list. And it tells us it's a doubly linked list implementation of the list and DQ interfaces. We don't have to worry about what that means. But there are things on top of which this is built. All the operations performed as could be expected for a doubly linked list. Operations that index into the list will traverse the list from the beginning or the end, whichever is closer to the specified index. Well, that's kind of cool to know, right? Because remember, we can in the linked list class we can say give me element 7, and so the author is telling us here that when we ask for element 7, we might start at the beginning and go forward 7 spots, or if the list only has 10 things in it, we'll start at the end and we'll go back 3 spots. Well, that's kind of nice to know. And this is all markup stuff, right? So this is a paragraph, this is bold-faced, and so on. The implementation is not synchronized, so it's not thread safe. If you have 2 threads interacting with a linked list, they could interfere with each other. So if you're going to do that, you need to synchronize the methods that are interfacing with that list yourself. And it talks about iterators and all this stuff, and then the name of the person who wrote this, and some other things to see, right? So that's all, you know, the comment block for the beginning of this class. And we've seen this before. When we pull up the Java documentation, right? Doubly linked list implementation of the list and DQ interfaces. All the operations performed as could be expected for a doubly linked list. Operations at index, etc., etc. Boldface, note that this implementation is not synchronized, right? That's this right here. There's the boldface, right? So this is the Java doc stuff that we've talked about briefly. Since this comment block starts with a /*, we can run the javadoc command on it, and it will create HTML, which, you know, gives you this view of the documentation. All right, and then here's where the class is actually defined, and it's generic, so it takes a parameter type E, and it implements some things and extends another class and so on. And here's an integer called size. Guess what? That's probably the number of things in the linked list. Okay. Do we need to know that? No. But it's there. So we can go through this code, but it's fairly wrapped up in other things. But something to note in here is that none of this code is particularly long, right? Here's 1, 2, 3, 4, 5, 6 lines of comments. Here's 1, 2, 3, 4, 5, 6 lines of code. Okay. The methods themselves, the thing that gets the first element of a list, is pretty short, right? Why? Because it already knows what the first element of the list is, and it sets that equal to f, and if that is null, it throws an exception. Otherwise, it returns the item field of that node. Right? That's what we've been calling a data field since 2.22. Right? There's a data and a next. Well, it returns the data item. Get last, same thing. It already knows where the last element is, and if it's null, throw an exception. Otherwise, return the data value. Now, why does it have a built-in header for the first node and another one for the last node? Just for efficiency. So that if we want to move backwards from the end, we don't have to go forward all the way to reach the end. We just have something pointing there. I don't know what transient is. I'm guessing... Where was it? I'm guessing it's kind of like volatile in that it's telling it that this value could change in certain ways, but let's Google that. Oh yeah. Okay. Serialization, right? There's a way to take an object and turn it into basically a bit stream that you can write into a file, and then later on you can read that bit file back and recreate the object. Okay, and when you tag a variable transient, it says record the default value of this variable instead of the value at the time that you serialize. And it's partially a security thing, and partially it just makes more sense then. So we haven't talked about serialization. All right, so short methods, right? Here's the append method, right? There's the documentation on it. Here's what it actually does. It calls add all, right? And where does it add it? Well, it adds it at a position given by size, and the thing it adds is the object C that you pass to the add all. So this is making heavy use of modularization, right? Things like add all that takes an integer and an object, right, are defined elsewhere and get used multiple times, and so any of the code we write is relatively small, right? This is a fairly complex routine. This is for removing an object from the list, right? And what does it do? It moves through the list, right, and looks for a place where the item, the data value of the node you're on is equal to the object you're looking for, and if it is, it calls unlink, which removes it from the list and returns true. If it comes all the way through and it hasn't removed the object, it returns false. You've written this code, right? This was your remove code that you wrote in 2.22 when you were putting together code for linked lists in C, right? You've done this. Start at the beginning and move through. Well, maybe you called search first, so you didn't have to deal with a special case. But, move through the list from the first node, and as long as you're not at the end of the list, keep going down, following the next pointer, and if the thing you're trying to remove equals this node's data value, go ahead and remove it and say success. Right? So you could write Java. You could do all this stuff yourself, and Java is, you know, the language in which Android is written. Right? So all the stuff that goes into making an Android phone work, and that whole infrastructure that comes along with that, right? It's all made up of, you know, these little 5 or 10 line modules, which are, you know, ODPs. This is stuff that you did in 222. It's not magic. Right? Here's a clear. Right, what do we do? Well, we set the data value to null, we set the next and previous value to null, right? And we do that in a loop. And then we set the first and last to null and the size to 0. But all of this stuff is hidden from the user, right? I don't know where to find these things, but these internals are like irrelevant to the person who's using this list, right? All the person who's using this knows is this stuff. Okay, I want a linked list. I'm going to construct it like this or that, and I'm going to add by doing this, and I'm going to add at the end by doing that, and I'm going to clear it out by calling this, and so on and so forth. Right, there's a clone method. This was final exam question, I think, from 222. Cloning a linked list. But they already have a clone method for the items themselves. Alright, so linked lists, kind of fun. Alright, here's a scanner. So lots of documentation in the front for the whole class itself. Right, because it's a complex method, a complex class, right? Because we can say has next double, has next byte, has next line, and so on and so forth. And these things have to be defined. Right, so what's a non-ASCII digit? What's a non-zero digit? What's a group numeral? What's a decimal? Right, it's an optional minus or plus, followed by a decimal numeral, followed by an exponent. Right, or it's this. This is like a little bit like BNF that we talked about in CSE 215. Right, this is a description of the syntax of the different kinds of things that a scanner will look for. And that's used in the code to do this processing. So there's a group separator, a decimal separator, there's a NaN string, and so on and so forth. And lots of regular expression stuff going on in here. Right? So digits. And why are those digits? Well, because if you're doing hex numbers, these things are valid digits, and if you're working base 18, then A through H are valid digits, and so on. All right, let's look at the string class. So, you know, usual boilerplate header block here not boilerplate, usual header block that tells you all about the string class. Strings are constants, their values cannot be changed after they are created. Examples of strings, description of the methods contained in here, and so on and so forth. authors. Class string. Final means we can't extend it. Private final character array value. I believe that's your string. I think it's an array of characters, just like in C. But guess what? We don't know that. We don't need to know it. We don't get to interact with that. This is a private variable. So if I have a string named temp, I can't say temp.value bracket 0 to see the first character of my string. It's private. It's an internal variable. Right? But this is where the characters are actually stored in your string. It's an array. There's a hash code associated with a string. It's stored in an integer called hash. There's a constructor. If we construct without an argument, this is funny. Here's a string that is empty, and we get the value of that, right? Which is this private variable, right? But inside the class we can access that. So how do we construct an empty string? Well, we make this string's value equal to the value from a string that's just comprised of nothing. A little bit of self-referential stuff there. If we have a string, we want to construct a new string, we take the original string's value and we copy that into this string's value. And we also take the original string's hash code and we copy that into this string's hash code. That's how we copy a string. So various ways to construct strings. How do we tell if two strings are equal? Well, if the object we're comparing ourselves to is ourselves, then the two things are equal, because we're always equal to ourselves. Otherwise, what do we do? Well, let's look at the length of this string, right? This string is an array, right? So array name.length tells us how many characters. So n is equal to the number of characters in this string that we're working with. And I look at the another string, right, which is the object that was passed in. If that string's length is the same, right, then I'm going to go through character by character and see if the two strings match. So I'll make a pair of character arrays, right, from those value arrays, and I'll iterate through from that length down to 1, and I'll compare character for character. And if they ever differ, I'll return false. If I get all the way through this loop and I haven't returned false, they must be the same string, so I return true. And if in fact their lengths were different to begin with, I just return false right away. So this is pretty straightforward code. There's details. If we have an object, we have to cast it into a string and so on and so forth. But you know, this is ODP level code, right? How do you tell if two arrays are comprised of the same characters and have the same length? Well, this is something like the code you'd probably come up with. What about the compare method? So find the length of our two strings, right? And we do that using the length method of the string, which just returns probably the length of the value array, right? Find the value of the smallest of those lengths, and then iterate over that. Take the characters at position I, starting with the leftmost character, and if they differ, convert them to uppercase, and if they differ, convert them to lowercase, and if they differ, then return their difference of those character codes. If we get all the way through this loop, it means the two strings agreed for the length that they had in common, and so now we just return the difference in their lengths. If they're the same length, then they're exactly the same, we return a 0. If the first string was longer, so hello versus hello there, right, and one would be smaller, this would return the difference in the length, so -5. So we can understand the inner workings of these methods if we want by going back and looking at the source code. And none of this stuff is particularly mysterious. Some of it's mysterious as to what it's supposed to do, like region matches. Here's the split method. So the split method again takes a string, which can be a regular expression, and breaks your input string into pieces and returns an array of strings. And it just calls a split method with a position of 0 for the starting spot. So it calls this code with a limit of 0. Something crazy going on downstairs right now. And this code's pretty hairy, right? Because this is the low-level stuff. This is the stuff that I always tell people not to try to do, because they should use scanf, or they should use split, or they should use regex, or something like that, right? But if you try to do something like take a string and split it up into substrings, separating it at spaces, right, this is the kind of stuff you'd end up writing. Alright, let's take a look at one more. Knew I wouldn't get that lucky. Let's take a look at a hash table. So you remember when we did hashes back in 222, the idea was to be able to take any kind of data, maybe like, strings or, binary trees or whatever, and store them in a way that we could easily retrieve. So we also thought of these as associative arrays. And so typically we had an array with some length to it, and we'd have some key 1, and we'd run it through a hash function, and it would give us an index, and that's where we would store key 1 and its corresponding value 1. And then if we had another key 2, we would hash that, and that would give us an index somewhere else, and there we would store key 2 and the corresponding value 2. And then if someone said, hey, what's the value associated with key 1, we don't have to search our entire array. We take key 1, we hash it, it comes over here, we say, hey, there's key 1, there's the value. Right, that was the basic hash table setup. And if we were chaining, then instead of storing the actual key value pair in this location in the array, we made this a header node for a linked list. And once we hash key 1 to this index, now we just search each of these to see if it's got key 1 in it, and if it does, we return value 1, and we're finished. So what does a hash table look like in Java? Well, it's an array. So it's a private array called table, and it's comprised of these entries, right, which are generic, because remember the key and the value pair can be any types of objects. So these are generics. But it's an array of these things, and it's called table. Well, we call it hash table, but the authors here call it table. That's your hash. And count tells you how many things you have stored in that hash table. And there's a note here saying that when the count exceeds the value of this threshold, the table is considered to be getting filled up, and it will expand the capacity and rehash. Right? So the table dynamically grows. If you need more space, it will increase based on how full it is and something called a load factor. So if our load factor is 75% and our capacity is 1,000, if the table size gets up to 750, it'll trigger a rehashing. And by default, it constructs a hash table with 75% load factor and an initial capacity of 11. How does it do that? By calling the default constructor with 11 and 0.75. So what does the get method do? Well, it makes a copy of the table. It takes your key and figures out the hash code corresponding to it. Okay, that's taking your key and running it through some kind of hash function to get an integer, which we call hash. And then we throw away everything except the 31 least significant bits of that hash code. So we AND it with, 3 ones followed by 28 more ones, so 31 ones, which gives us an integer between 0 and about 2 billion. And then we reduce that modulo the length of our table. So if our table has 11 entries, whatever hash code we come up with has to be reduced modulo 11 so that we get a number between 0 and 10. Well, that's what's happening right here. And so index is where in the table it should find our key if it's stored in there. And now we do some looping around and we check to see if the key that's stored is the same as the key that we're looking for, and if it is, then we return the value of that entry. And if we get all the way through this loop and we haven't found the key you're looking for, we return null. Okay, that's your hash code from Winter Quarter. So let's look at one more thing. Let's look at this hash code. So key is an object of type object. Why? Because we could be trying to get anything that we want, right? We could be keying off of a string or an integer or a rectangle or whatever. The most general category of what we're looking for, though, is an object. So this object should have a hash code method associated with it. Let's look at the object class. And it tells us object is the root of the class hierarchy. Everything is either an object or an extension of an object. And I think nobody took credit for writing this, which seems appropriate. Alright, so this tells you about the hash code. Let's look at the actual code for it. Guess what? There's no code in here. There's a declaration that hash code is a public method. It returns an integer, it takes no arguments, but it has the keyword native. Which means this is not written in Java. It's written in the native language of the JVM, something like assembly language. Okay? Why? Because this is such a low-level routine that we can't write something in Java very well that will give us the hash code of an object. the hash code is related to things like where the object is stored in memory. Okay, because the hash codes are supposed to be unique for every object. And so this is a low-level routine. But we can get some hints to what the hash code looks like if we look at the toString method. So what does toString do? It returns the following string: the name of the class, an @ sign, and then a hex representation of the object's hash code. So now at the end we finally know when we say print line and we put in the name of an object that doesn't have a natural representation in human readable form, and we get this funny thing like rectangle, @ sign, and some hex number. That hex number is the hash code of the object. And if we make a different rectangle, we'll see a different hex code. And that's the hex code that's used, that's the integer value that's used when we try to make a hash table and store that object in our array. That's the code that's going to be used, reduced modulo the size of the table, and used to find an index wherein to store this object. And a lot of times when you're digging into code like this, you get to a point where you reach something like a native function. Okay, for example, if you want to look at source code for C, you can find the source code for the fgets function. Okay, which is really just a wrapper around gets, or gets is a wrapper around fgets, and fgets is really a wrapper around read, right? The manual pages chapter 2 version read, which is this low-level thing for doing byte by byte input from some sort of file descriptor. But if you look at the source code for read, it's not going to be written in C anymore, because at some point something needs to talk to the lowest levels of the hardware, and the source code for read is probably just a software interrupt, right? Because we cannot write C code that directly goes out to the hard drive and starts reading information from a particular sector or cylinder on the hard drive. That's a security issue. We cannot write C code that will just arbitrarily go out to the network and grab information that's coming in. That's a security issue. So those kinds of accesses are controlled by the operating system, which means our read function, for example, needs to interact with the operating system. And it needs to do that in a controlled way, and that usually means throwing a software interrupt or an exception. So the read code will set up some values in memory indicating what the request is, and then it'll request an interrupt, and the operating system will respond to that, see what's been set up in memory, and take whatever action is appropriate, including possibly saying permission denied. Right? And so these native methods in the Java source code are similar. They're written at a lower level, and they interact more directly with the virtual hardware of the Java virtual machine to do things like low-level I/O or computing hash codes or things like that. So this can be fun stuff if you're looking for things to do over break or over summer to stay up to speed on programming. Digging around source code is not a bad way to spend some time, right? You can take this code, you can make a copy of it, change the name, modify it, make your own version of the string class or the hash table class, right? Try to break it. It's fun to break stuff. Make something that like every time you make a string, it actually comes out backwards, right? And then throw that into some code you've already written that uses strings, and watch your word index come out backwards. Whatever. It's fun to experiment, and open source stuff is so amenable to experimentation that you can potentially have a lot of fun with it. And if you want to write your own language, you know, you can do that too. Kotlin's another language that runs on the JVM. You could make your own version of a language. You could port Rockstar to the JVM, which would be really awesome. So lots of things to explore and play with. Alright, so I've posted a quick list of topics on Canvas for the final. We can run through those tomorrow. If you have particular questions, of course, we can always talk about those. Office hours today at 3, tomorrow at 11 and 3, and that does it for spring quarter. Final exam on Monday, and then we're done. All right, sun is out. Have a great afternoon. I will see you next time.